So good afternoon, sir. My topic is all about weight measurement. So my subtopic are spring scale, analytical balance, multiple lever system, and pendulum scale. So the first one we'll talk about is the spring scale. So spring scale or Newton meter is a type of mechanical force calculation weighing scale. It consists of a spring fixed at one end with a hook to attach an object at the other. It works by Hooke's law, which states that the force needed to extend the spring is proportional to the distance the spring is extended from its first position. So therefore, the scale markings on the spring balance is equally spaced. A spring scale cannot measure mass, only weight. So this is a picture of spring scale. It is how it looks like. So the next one is the uses. Main uses of a spring balance are to weigh heavy loads such as trucks, storage silos, and materials carried on conveyor belt. They are also common in science education as basic accelerators. A spring balance is measures the weight of an object by opposing the force of gravity acting with the force of an extended spring. So I have here example or a problem on how much force is needed to pull a spring with a spring constant of 20 Newton per meter and a distance of 25 centimeters. So the formula we're using is F equals negative K times triangle X. So this is the formula of Hooke's law, which is F is the restoring force of the spring I mean. Then K is the proportionality constant called the spring's constant. Then triangle X is the change of the spring position due to the deformation. So the negative sign in that formula is showing that the restoring force is opposite to the deforming force. So in my problem, there was no negative signs, meaning my restoring force is not opposite to the deforming force. So first one is 20. So we're now find the force. So the formula is F equals K times triangle X. So K there is 20 Newton per meter. Then the triangle there is the 25 centimeters. So we'll now convert this. It will become 0.25 meter. So 20 Newton per meter times 0.25 meter equals 5 newtons, which is the answer. Then the next one is 20 Newton per meter, which is the same result with the first problem, which is the constant spring constant, then times 0.15 meter equals 3 Newton. Then the third one is 10 Newton per meter times 0.20 meter equals 2 Newton. Then I have another example here. We will now find the spring constant. So the formula is F divided triangle X equals K. So 500 Newton divided at 0.10 meter equals 500 Newton per meter. So the spring is pulled to a 10 centimeter and held in place with a force of 500 Newton. What is the spring's constant? So as what I have discussed kanina, so use as the 500 Newton divided 0.10 meter equals to 5,000 Newton per meter. Then the second one is 100 Newton divided 0.05 meter equals 2,000 Newton per meter. Then 200 Newton divide 0.25 equals 800 Newton per meter. Then I have So the next topic I have here is the analytical balance. An analytical balance or a lab balance is a class of balance designed to measure small masses in a sub-milligram range. The measuring pan of an analytical balance is inside a transparent enclosure with doors so that dust does not collect and so any air current in the room do not affect the balance operation. This enclosure is often called a drop shield. So this is the analytical balance looks like that one. Then this picture in the lower side is an analytical balance with its part. Then analytical scale measures the force needed to count the mass of a sample rather than using actual masses. They use an electromagnet to generate force to count the sample and output the result by measuring the force needed to achieve balance. The measuring pan of an analytical balance is inside a transparent enclosure with doors, as what I have said a while ago. So environmental influences are blocked. That means dust does not collect and so any air current in the room do not affect the weighing performance. So this is means that kanang magtimbang o gamiton ang analytical balance in finding the kabugat sa kabutang need siya nga close ang iyahong operations kay para dili maka-apekto ang abog or kanang hangin. So the uses an analytical balance is a basic tool in all quantitative analysis. This balance provides accurate readings in education, research, industrial, or quality control application. The analytical come with many features and functions. Most of them having counting and checking counting application, for example, this can be useful when counting pills, ingredients, or very small pieces. So meaning ang analytical balance which is count lang siya for small pieces or gamay ra kabutbut. So I have video here that will explain all about analytical balance.
Most commonly used pieces of equipment in biotech laboratories is called an analytical balance. We can use it to take very precise measurements. 4 places to the right of the decimal point. Keep in mind that a small paper clip weighs about 1 gram. In other words, the analytical balance isn't designed for weighing heavy items. For example, this balance has a maximum weight of 310 grams. That's about the same weight as a can of tomato soup. Weighing anything larger than that will cause damage. The first consideration is selecting the workspace. The balance needs to be placed on a steady surface such as a marble counter or a lab workbench in order to minimize vibrations. The balance shouldn't be used near doorways or air vents because it's sensitive enough to be affected by air currents. Check to see if the balance is level. Adjust the feet until the air bubble is inside the black ring. If the balance has been unplugged or turned off, you need to let it warm up and reach the required operating temperature. Let's try an example. We want to measure out 1.5 grams of sodium bicarbonate. Typically, we use weighing paper for measuring anything less than 5 grams. Fold the opposite corners of the weighing paper together and make a crease. Then do the same for the other corners. Place the paper on the balance pan. Close the side doors and press the tare button to zero out the paper. Use a lab scoop to slowly add the sodium bicarbonate to the paper. Close the glass doors and wait for the balance to lock in its reading. Continue adding sodium bicarbonate until you reach 1.5 grams. Close the doors to read the actual weight, 1.5026 grams. And always document your work in your lab notebook. Let's do another example. This time, we'll weigh some something a little heavier, so we'll use a weighbow instead of paper. Let's measure out 12.19 grams of powdered tris buffer. Place the weighbow on the balance pan. Close the side doors and press the tare key. We're aiming for 12.19 grams, so the measurement should be within plus or minus 0.02 grams. Always document your work in your lab notebook. Cleaning the balance is an important step, especially at the end of the day. Put it into standby mode or unplug it. Remove the weigh pan and components by lifting straight up. Use a very soft bristle paintbrush to sweep off any powder remaining inside the weigh chamber and in the grooves for the glass doors. Once it's clean, replace the drip ring and the weigh pan. Now you're ready to head into the lab and practice using an analytical balance hands-on. To find a life science course near you, visit ncommunitycolleges.edu or ncbionetwork.org.
So that is how an analytical balance will be used. So the next one is multiple lever system. So this is a picture of it. That one. Then the system is provided with an adjustable counterpoise, which is used to get an initial balance. Therefore, the unknown load is applied to the platform. The poise weight, or the WP, is set at 0 WM scale, and counterpiece is adjusted to obtain initial zero balance. In order to simplify the analysis, it is assumed that the weight can be replaced by two arbitrary weights, which is weight 1 and weight 2. Also, it is assumed that the poise weight is at 0, and when the unknown weight is applied, it is unbalanced by weight in the pan. So this is the light uses of the multiple lever system. This one is the weighing scale na gamiton usually sa mga bugas and sa kupras. Then the other one is in heavy uses. This one naman ay sa timbangan siya sa truck. Ano siya usually gamit. So I have video here that will explain all about the multiple lever system.
In this video, I will explain compound lever balance for measuring weights. It is preferred for measuring large weights. Here, two smaller weights, this poise weight and this pan weight, are used to measure a large weight W which is kept on a platform. It is shown here like this. Usually, this balance is used to measure weight of trucks. Now, it is not always possible to keep the truck exactly at the center. So, this balance is designed in such a way that even if truck is not kept at the center, this balance will give the correct result. Now, let us prove that position of weight does not affect the measurement of that weight. For that, I have drawn free body diagram of beam scale, this beam scale. Now here, this weight, this poise weight, its moment is balanced by adjustable counterpoise. So initially, moment of this poise weight is adjusted using this adjustable counterpoise. So moment of this and this are same and opposite in direction. Therefore, they balance each other. So I have shown only the force, that is, this is a tie rod which is placed here in vertical position. Now there will be one tension in tie rod T, this force, vertical downward direction, and there is another force, pan weight Wy, which is acting like this. Now if I take moment about this point, this particular point at the point of support of this beam scale, So you can take that moment, anti-clockwise moment, this is anti-clockwise moment of T will be anti-clockwise and moment of Wi will be clockwise about this point. So anti-clockwise moment is equal to clockwise moment. So accordingly you will get T into B, T into perpendicular distance B is equal to Wi into A. Now this W is distributed as W1 and W2. If this W is at the center, then W1 and W2 both will be same and equal to W by 2. But if it is not in center, then it will be different. But W1 plus W2 will be equal to W. Now this W1 is transferred to this second platform, and this second platform is supported at this main lever. So now we will draw a free body diagram of this main lever. In this main lever, this lever is attached here with this tie rod. So here one tension will occur, and one force, one load is applied here at this point, and another load is applied at this point. Now this load W2 is a part of this W which is applied here. Now we have to determine value of force occurring here. For that I will first make free body diagram of this platform 2. So this is platform 2. Now you can see that here two supports are there, one support here and one support here. So there will be two reactions, one here and one here, and one load is applied at this point which is equal to W1. So I have applied this load W1. Now distance of this W1 are given from here. This distance is F. So where distance of W1 from this point is F, and distance of this support from this point is D here shown. So this I have drawn D. Now you can take moment of all the forces with respect to this point and equate to 0. That means clockwise moment is equal to anti-clockwise moment. So if you take this moment with respect to this point, then W1 its moment will be clockwise and R its moment will be anti-clockwise. So when you use this moment balance method, so you get this R is equal to, that is R into D is equal to W1 into F. So R is equal to W1 F divided by D. Now this R is transferred to this main beam. So let's draw free body diagram of this main beam. So I have drawn free body diagram of this main lever. So here one tension T same which is applied here, because these two will be equal and opposite. In beam scale we have applied one tension T here in vertical and downward direction. So the same tension we apply here in upward direction T. Now this load at this point we have already calculated, which is equal and opposite. This R is acting vertical upward direction on this platform 2. So R will be vertical downward direction in this main lever. And third one is W2, which is applied at this point. So I have drawn this W2 applied at this point. So there will be one reaction R dash. Now we are going to determine moment of all the forces with respect to this point. So moment of R dash will become 0 because it is passing through this point. Now this T is clockwise with respect to this point. When you take a moment of T with respect to this point, then this will be clockwise direction. So this is clockwise, and these two will be anti-clockwise. So moment of T must be equal to moment of this force and moment of this force. So that's what I have written here. T into C, perpendicular distance, is equal to, this is the force W1F divided by D, this is the force, into its distance is E from this point, and similarly W2 is here, and this distance is H. Now here I have taken out this H, so I have taken out this H, so this will become W1F divided by D into E divided by H plus W2. Now we can design we can select the value of F, D, E and H in such a way that F by D is equal to H by E, so that multiplication of F divided by D into E divided by H should be 1. So this equation will convert to T into C is equal to H. Now this term become 1 because we have designed in such a way that these two are reciprocal. And so W1 plus W2, now we know that W1 plus W2 is equal to W, so this becomes W into H. So this tension is independent of, the tension which is applied here is independent of its position. Wherever you want to place this W, you can place in this platform. Ultimately tension, there will be no effect on the tension which is coming in this tie rod. From first free body diagram, we obtained this relation T into B is equal to Wy into A, and from the second free body diagram of this main lever, we obtained T into C is equal to W into H. Now, so T is equal to this tension in tie rod is equal to WH by C, and here T is equal to Wy A divided by B. So equate these two T together. So what we will get, that is Wy A divided by B, Wy A divided by B is equal to WH by C. So this W can be calculated. So this W is equal to A by B into C by H into Wy. So this A, C, B and H, these all are constants. So W is directly proportional to Wy. So whatever pan weight is there, accordingly you can determine what is this actual W. Now this A, C, B, H, we can take one example. Suppose A into C divided by B into H. So this is my A divided by B, this smaller one, larger one divided by smaller one, into this C, larger one divided by H, this smaller one. So suppose A and C both are larger and B and H are both smaller compared to these two. Now suppose value of this A into C divided by B into H is 100. That means at that particular time, if weight is 1 ton, then that 1 ton weight, if this weight is 1 ton, that 1 ton weight can be adjusted using only by a 10 kg weight. So only 10 kg weight is sufficient to balance a 1 ton load. Accordingly, we can determine whatever weight is there based on the pan weight. Thank you for watching this video.
So the last subtopic I have is the pendulum scale. So weight measurement device in which the load is balanced by the movement of one or more pendulums from vertical zero weight to horizontal or the maximum weight. So ganin mo siya, this is a picture of the pendulum scale, that one. So I have video here. It will show how pendulum was laid. So just watch it for a little bit. I hope you learned something from my discussion. So